All right, we need to take another day and talk about continuity or continuous functions. And there's a couple of things that we just need to clean up. Some of them are properties. Okay? And what these properties say is that if I have two continuous functions, if f and g are continuous, and we'll just abbreviate here, at x equals c, then, big word, then, the following are also continuous. Okay? That's supposed to be a following with a G on the end. So, if f and g are both continuous at a certain value, then guess what? So are f plus g, and f minus g, and f times g. Okay? All of those are still continuous. Even f divided by g is, so long as g of c is not equal to 0. G of c is that place that we're looking at the continuity. Obviously, we can't have a denominator of 0. K times f, or k times g for any number. You know, k is our kind of our universal symbol for a constant. Okay? If I multiply any of them by some number. And also g of f and f of g would all be continuous. All right? So the way this helps us is if we get a problem like this one. Show that this ugly beast, y equals the absolute value of x sine x all over x squared plus 2. Show that that ugly beast is continuous. It's amazing how I can call these functions mean and nasty names and they just never reply. But that's okay. That's the world of math that we live in. So if you look at this ugly thing, it looks really bad, but not if we break it up into a bunch of pieces. Look, if I think of f of x as being the absolute value of x, all right, kind of the outside type function, and then I think of g of x being what I plugged in. Remember, f of g and g of f are continuous if g is continuous. Okay? Now, isn't this thing on the right, isn't this thing just several functions kind of multiplied and divided together? So let's break it up into pieces. Okay? How about the function, I'm just going to use some different letters here. Is h of x equal to x continuous? Is the function x continuous everywhere? Yeah, it's just a simple linear. Continuous, check mark. How about r of x is sine of x? Is sine of x continuous everywhere? Sure is. Check. How about, I'll pick another letter, q of x equal to x squared plus 2. Is that continuous everywhere? It's just a parabola moved up 2 units. Yes. And here's a more important question. Is this one, since it's in the denominator, is it ever equal to 0? Think of your function. Isn't it a parabola moved up 2 units? It is. So this one is never 0. Okay? So because this g of x is just what? H of x times what? R of x over Q of x, right? And every one of those pieces is continuous, then that means G is continuous, right? And this thing up here is just f of G. Okay? Oh, we forgot to talk about the absolute value function. Is the absolute value function continuous? It is. Okay? So every piece of this thing is continuous. So you have to break it up and look at every piece. Now I want to talk about our next piece of cleanup detail, endpoints. And we kind of ran into this continuity at an endpoint. I told you we would talk about this. I'm just going to give you the definition. A function is continuous at a left or right endpoint if it's a left endpoint, all right, then it is continuous if the limit as x approaches a from the right of f of x equals f of a.
So it's continuous?
It is continuous at a left endpoint if that is true. And let's just do a quickie example here so that you're not swimming in all of the words I'm giving to you. How about our old friend, the square root function? This was the one I talked about the other day. And let's say that we had the square root of x minus 2. Okay? So that would be here, boom, like that. So, is this function continuous at 2, according to this definition? It is, right? Because the limit of the square root of x minus 2 as x approaches 2 from the right is the same thing. What is it? Isn't it 0? Right? As we approach 2 from the right, the limit of the function is 0. And isn't that the same thing as f of 2? Right? F of 2, you'd plug in the 2, 2 minus 2, 0. All right? So this one is continuous at the left endpoint. The right endpoint is exactly the same definition, just going the other way. It would be the limit as x approaches a from the left of the function equals f of a. Okay, so that's kind of like if you had a square root function that was turned around the other way. All right, if you had one like this. Right? That one would be continuous over at that right endpoint. Okay? Very important. How about interior points? Now, this is kind of what we've already stated, but sometimes they start talking about the middle points, okay? And this is just the normal definition that we follow. If we're talking about the interior points of a function, what am I talking about? Maybe we've got this function, you know, one of these crazy piecewise defunctions. That's funny. Defunctions. That looks like this. Okay? All right? So it's cut off on both ends. How do I know if it's continuous in here? Well, it's the regular definition. Okay? So I just wanted to clarify that. Now, an important, very important theorem. The intermediate value theorem. Sometimes called the IMV. And we're going to learn two different theorems this year that have the word value in them, and we have to keep them straight. This is the intermediate value theorem. Later, we're going to learn the mean value theorem. Okay, so we have to keep these two straight. Now, here's what it says. It has a big, long definition, okay? But I'm going to give you kind of a shorter definition. The idea is, if I have this function from A to B, okay, there's my function, all right? In general, what the intermediate value theorem says is that if this function is continuous, and this is why we're talking about it now, okay? If f is continuous, okay, because that's the whole, foundation for this thing. This function f has to be continuous, all right? Then there has to be a place, okay? This value right here, isn't this called f of a? Isn't that value f of a? And isn't this value up here f of b? Okay? If this function is continuous, then there has to be a place in between those two. Okay? F of c. There has to be. It has to go through f of c to get to f of b. This function, when it leaves f of a, it travels along this line. If it is continuous and it goes from this f of a up to this f of b, it has to go through f of c. Okay? So, in other words, it takes on all the values in between. The function, it being the function, f of x, takes on all the values between f of a and f of b if it is continuous. All right? If it is continuous, it will at some point go through f of c. Okay? Has to. And that is what the intermediate value theorem says. So, if I had some function, some ugly thing, let's say it's this big ugly polynomial, x to the fifth plus 2x to the fourth minus 6x cubed plus 2x minus 3, okay? And I was told on this interval, -1 to 2, I want you to verify the intermediate value theorem. Verify the intermediate value theorem on that interval. Well, what I would do is I would start with my endpoints. Let's see what the function values are at the endpoints. And I'm going to save you some time here because we're running out of time. I'm just going to tell you that f of -1 is 2. Okay? And that f of 2 is 17. All right? So what the intermediate value theorem says is that there has to be a number c, okay, somewhere in between these two that will give me a number in between 2 and 17. There has to be at least one. and then you have to find that number. How could we find that number? There's a number of things you could do, right? Couldn't you consult the table? Couldn't you consult the graph? Isn't this thing a big, long, ugly polynomial? So this is a good place to consult a graph and see what's going on. But there is at least one number, f of c, in between f of 2 and f of negative 1. Okay? And then we would need to find it. And probably the best thing I can tell you is to verbally nag a little bit. Okay? Consider it numerically, consider it graphically. We're probably not going to consider this one analytically, are we? Because it's a big, long, ugly polynomial. All right? So once again, the intermediate value theorem says it takes on all the values between f of a and f of b. Okay? If it is continuous. All right? And we will stop there for today.